Hello, welcome to session number 18 in the series Analog Circuit Design using ADS. Myself Anurag Nigam, and I just want to continue with the treatment I'm giving for bipolar junction transistor. It's a very important device when it comes to power amplifiers and stuff like that. So that's why a detailed treatment is required, and I would say that all work and no play makes a designer a dull boy, so I don't want to be a dull boy, so let's do some playing with the simulator. So I'm going to make a new folder. It says BJT. So I'm going to investigate a BJT. Okay, so what I'll do is I'm going to make a new schematic, and I will say NPN characteristics. NPN characteristics. Okay, so I'm going to make a new schematic called NPN characteristics. Okay, so I am going to use, so there are a number of models for devices. There are models, right? For example, we have been using for FinFETs we have been using BSIM-CMG. For some of the MOSFETs which are like 130 nanometer, we are using BSIM-4 models. For IO devices we are using BSIM-3 models. And so for a bipolar, the simplest is a Gamal-Poon model. Then there are certain other models like compact models like Webic, right? So we are going to use a Webic model in here, right? So let me get a Webic model, right? An instance of a Webic. So I have to go to devices. Let me see if there is devices. BJT, right? So that's the device, and I'm looking for an NPN Webic. So see, there are different models here, right? So I have fitted a Webic model, right? So let me grab a Webic NPN. So that's a Webic NPN, right? Oh, there is a temperature here, so I don't want to put in a temperature. Let me look for a model without temperature. Yeah, this Webic NPN. Okay, so if your DC coefficients and RF coefficients are scaled with temperature, you can use that. Or there is another way of specifying device and simulation temperatures. Okay, so in this case, okay, so let's see what are the parameters. So I have a PDK, so I have fitted a model, a Webic model for a silicon germanium device. So let me see library files, study PDK, right? So here I have done a Webic model. So just go inside here. Okay, so there is a bipolar model which is called a Webic model, right? And this is a very complex model, so I'm not showing the details of this. Okay, but then it allows you to do across process variations, right? It allows you to do across temperature variations. So it has everything built into it, and this is coming from an IBM process, right? So this is called Webic. So this is called HBT NPN, right? So I will have to call that model as HBT NPN. So this model I have to call as HBT NPN, right? So that's there. Now let's go here and see what is a scale. Okay, so a scale and multiplicity, right? Okay, so what I have is this is a 0.5 micron width, which is fixed here, and then I'm scaling the length, right? So let's consider something like 5. So I have 1 micron as the width. So now if I scale with 5, it will be 5 micron, right? And then I have a multiplicity, right? So let's say that multiplicity is 40. So these are 40 emitter fingers. Apply. Okay, so 5 micron into 0.5 micron into 40, right? So it is 2.5 into 40 is the micrometer square area. 2.5 into 40, correct? So that's going to be 100 micrometer square. Okay, so done that. I will just display what I want to display in this case. So I will just display the model name, the scaling factor, and the multiplicity or the number of devices in parallel, and that's it. Okay, and then we know that this basically, if it was to sit in the well, we could have just shorted this out, or we will connect this to ground. F5 to move the text. Okay, and I'm going to short this to ground. Okay, the way an analog designer biases a transistor is slightly different from the way the RF designer biases a transistor. And RF designer is more concerned about instable or oscillations on a big device. So this is not a big device, but usually they try to place the device to a impedance of 50 ohms when they do the DC parameters, right? So this is because the expectation is that the center of the Smith chart is going to be the most stable portion, right? While the periphery, right, is going to be the least stable. And when you do analog design, right, you tend to just directly put here, let's say you tend to just put here the DC source, and as soon as you put the DC source, it means that you are creating a RF short, right? So RF short means that's a reflection point, so that's not going to be a stable area, right? So what I'm going to do is I'm still going to put a choke here and terminate it into 50. So I'm going to go to lump components, DC feed, and the reason I'm doing this is because in case the device oscillates, then its DC parameters are not going to be correct, right? So let's just put this for namesake, assuming that this is a big device. Okay, now a transistor can be biased in two ways. Okay, one is I can use a voltage to bias it, other is I can use a current to bias it, and there is a vast difference between the two in when it comes to linearity and breakdown. So I'm going to bias with a voltage first, and later on I'm going to bias it with a current, so that you can see the difference, how the BJT is going to behave. And let's put here a DC block in here and DC block here, and then terminate this into 50 ohm RF wise. So I'll take two terminals out of S parameter. I'll take terminal 1. This is how you RF designers see it, not the analog designers, because RF designers are more concerned about stability. And you know, all those ways in which these elementary books teach you to bias a transistor, like the resistive bias, resistive divider, self bias, and all that. When I was a student, I studied that, but that's not how a device is used in the industry, right? That's not how it is biased, right? So according to me, all those questions in the undergrad, they are bogus actually, and also in the gate curriculum, they are kind of bogus. Okay, so I don't agree with putting resistor in the load and saying that the gain of this amplifier is this. So I really don't like the treatment they do in the undergrad using resistive dividers for biasing a bipolar. That's not how the things work. So I can't say throw out Sandra Smith, right? Because Sandra Smith is people learn some concepts, or throw out Millman Hill case, okay? Because those are old authors, right? Okay, so what I'm going to do is I'm going to put in a probe here, a probe component. So where do I find the probe components? Probe components. And why would it Come on, this is so horrible. Okay, the anticipated direction of current is going to be flowing into the collector, so I would have to put a mirror on this. Sorry. So probe component, I have to put a mirror on this like this, and this is going to be collector current IC, right? And then I'm going to put in here the voltages. Okay, so forces frequency domain, I'm going to put here a voltage here. Okay, IC is equal to beta IB, right? So if, for example, I'm going to operate this from 3 volts, okay, and or rather I'm going to operate it from VCE, right? So because I have to plot the characteristics, VCE, and here I can do a current bias, right? So let's say IDC, okay, and this is a current, right? So it doesn't matter where it draws the current from. That's there. Now this I can put as IB, correct? So IB current, I'm going to step and I'm going to see IC versus VCE, right? So let's put here a DC simulation DC. So go to DC and put here DC controller, and here you put here IB, sorry, parameter to sweep is going to be IB. Okay, so I'm going to go from, so if I go from 10 micron to 50 microamps, so then 1000 times of 10 would be, okay, 1 micron would be 1 milliamps, right? So let's just do this. Let me go from 10 micron to 20 micron. So I'm going to go in the output. So 10 micron to 20 micron is the current. No, in this, because I'm going to sweep VCE first. Okay, so VCE I'm going to go from 0 to, let's say, 3.5 volts, and steps of 0.001. Okay, and that's okay, and I'm going to put here VB, so that I'm also plotting what is happening to VB. Name here. So I'm also going to observe VB here. Okay, now, okay, so here I'm sweeping that, so let's display this. Okay, and then I'm going to have a parameter sweep. Here I'm going to sweep IB, right? Let me see if I'm recording. Sometimes, yes, I'm recording. Okay, so here I'm going to sweep IB, and the IB goes from 10 microamps to, okay, 10 to 20 microamps, 20, right? In steps of, let's say, 2. Okay, and here I have to put in a unit of microamperes. Okay, so that's there. Now one more thing is I have to declare the variables. So there are 2 variables which I am sweeping. Okay, one is IB, so let the default value be 1, and one is going to be VC, let the default value be 1, VC, correct? These are all case sensitive, so make sure that you put the right thing. Okay, so again I have to also tell where is the inner loop. The inner loop is inside DC1. Okay, so once I've done that, let me hit simulate. Okay, so if all goes well, I should see the familiar characteristics. Okay, so I'm going to plot IC versus VCE. So IC versus VCE. Okay, these are the curves. So it has gone into breakdown. So let's do this up to here. And second thing is I want to, yeah, so let's just do it up to 3 volts or 3.3 volts, right? Okay, so VCE, let's go up to 333 volt, right? And hit simulate. Okay, okay, that's the story. Still it is way up, so because let me just see again, where is it? Okay, so this is entering breakdown, and the beta is around, so if it is 10, for 10 I'm getting, so I see, let's put here the units, format auto engineering, so I'm getting 1.1, so 114 is the beta roughly, right? So 114 is the beta here. Okay, anyways, so let's go another thing, let's go up to 30 and step size of 4. That's okay. Let's see what happens now. Okay, so now for this I want to see what is happening to VB, right? And this I'm going to put on the right axis. Okay, you would notice one thing. Okay, so VBE is a constant here, isn't it? Let's see, let's put a marker here. Okay, so I will prove one point here. Okay, so you see 2 and 3. Okay, so what do you see? VBE is from 0.768 to 0.797. And how many steps I have taken? I have taken 6 steps. Right. Now notice what happens to VBE over here. Okay. What happened to VBE over here? Okay. And why I'm saying this? Okay. What is happening to VBE over here? VBE is rising. Why is VBE rising? Because there is no hold on what the gate voltage should be. So when you increase collector to emitter voltage, so when you increase collector to emitter voltage, you are increasing collector to base voltage, fine, but you have no control over this node voltage. You are letting it float, and that voltage is going to increase VBE. So that increase in VCE is going to contribute not only to the increase in VCB, but also going to contribute the increase in VBE. So what does it tell you? Okay, so that tells you that you are not able to pull out current from the base. The base current is going back into the emitter junction. So if the current which is supposed to leak out of the base is now going back into the base emitter junction, it is not happening because there is a current source here. So biasing with current is like the breakdown which you are going to see under this condition when you bias with current is base to emitter junction. Okay, so that will be VCEO. Okay, that is basically BVCEO. That means that it is base to emitter breakdown with base to collector base to emitter breakdown with it will be a collector to emitter breakdown with the base open. Okay, collector to emitter breakdown with the base open. It means that you are not going to get the current to flow in here. So I'm going to derive it. Okay, so but I'm going to put down the expression. Okay, so here. Okay, so I'm going to derive this. Okay, so what point I'm driving here is this. If you bias it with the current, so what you're going to observe, bias BJT with current source. Okay, so this is equivalent to, so the breakdowns we are talking about here, that's the major difference I'm going to see. Breakdown voltage in this condition is BVCEO. Collector to emitter breakdown with base open. Collector to emitter breakdown with base open. Okay, now what is happening is, in a device, okay, when this junction starts breaking down, the current IB is going to turn negative in case I can absorb this. But because I have a current source here, there is no way for the current to reverse direction here. So there is no way for current to reverse the direction. So all that current has to go back into base emitter junction, and this additional IB will cause IC to go up again. So this results in what is called thermal runaway. Okay, so this is the major cause of the breakdown of the device. Now, if I was to bias this transistor with a voltage source, okay, so instead of this I had this. Okay, so this will be VB plus minus. Now in this case VB could swing, right? In this case my IB can change, it can become negative. Okay, so the current is going to be grounded by this DC supply, right? And that would not cause that current to flow into base emitter, and that will keep IC to be, IC not to run away. Okay, so the IC is not going to run away in case of you bias it with a voltage. Okay, so this runaway will occur at a much higher voltage. So that voltage would be equivalent to, so now when you bias this with a, so let me put that here also, bias the BJT with voltage source, right? Okay, now what is that? That is going to, that the breakdown what you're going to see here is going to be the collector base junction breakdown. Okay, that is going to be at much higher voltage, so that would be BVCBO. This is collector to base breakdown, the collector to base breakdown. So I'm trying to explain to the designers that there are two ways to bias a BJT, and both have its pros and cons. Collector to base breakdown with emitter open. Okay, so now the relationship is BVCEO is equal to BVCBO under root of beta f, and in this case beta f is around 114, so square root is roughly 10, so roughly 10. Okay, so mind it, that's what's going to happen. Now this may not be a square root, this may be the nth root, so it may be, instead of, it may be the cube root, right? So in that case this will be less than, yeah, so you can do that, cube root or whatever, right? Square root. So square root is 10. Now let's see. Okay, so now what is the difference here? The difference is, in the case of bias with current, the voltage at the base can swing. So if you increase VCB, it's going to increase. If you try increase VCE, not only VCB will change, but VBE will also change, right? Because now the current is not going into the current source. It has no way to go into current source. It will go into the base emitter junction and cause a runaway, and that is the cause of this early breakdown, right? Now notice this, we have VBE going from 0.768 to 0.797. okay, 0.768 to 0.797. so I'm going to just cross this for a moment. Okay, and I'm going to put here a voltage source voltage. Source is frequency domain. Okay, I'm going to put here a voltage source. Okay, and then I'm going to have 6 steps of this voltage. Okay, and I'm going to call this as VBE. Correct? And I have to declare a variable here, VBE. Let the default value be 0.5 and say add, and then I am going to sweep here VBE, and I'm going to sweep from these values 0.768 to 0.797, 0.768 to 0.797, 797, right? And I want 6 points, so you decide what the steps I should be, right? Understood that? Okay, so I'm going to do that. Now I am going to change the data set so that I can compare. So I am going to change the data set, and also I want to measure the current flowing in, right? So I would here put another probe. So I'll put here a probe component. Okay, this is something what I'm trying to show you, which most of the books can't show you, and most of the people who train on YouTube can't show you, because they don't have a simulator to show you. You understand what I'm saying? So I am looking at the base current IB, which will be flowing in, right? So let's say I call this as IBB. Okay, because IB is named here, I'm going to name this as IBB. Okay, so now I am going to change the data set, and I will call this underscore V, and say apply, cancel, and say simulate. Okay, no, and now I'm going to plot here from the new data set. I'm going to plot here the collector current. Just 1 second. What have I plotted? Just 1 second. Okay, I'm putting the current on the right hand side axis, right? So that, you know, I'm going to make this green color so that it is clearly visible. Okay, so what do you see? You see here the endpoints are going to be, of course, if I have to do this correctly, I would have to measure each base point. So let's do that. Why do I even do this? I'm going to use a sweep plan. and I'm going to put here a sweep plan. DC simulation sweep plan. Is there a sweep plan here? Yeah, sweep plan. I'm going to put each voltage. Okay, I'm not going to put linear, I'm going to put single points. So first point is, so I want the graphs to overlay. That's why I'm doing this. So the first point is 0.68. The second point is 0.77. So 0.68. 0.68. Right. The next point is 0.77. 777 or 77 only. Let me just see. 777. Okay, apply. No. Let me just go back and see. This is 0.768. 0.768. And then 0.777. 0.777. And then add. And the next point is going to be 0.784. 0.784. I'm taking this pains to just make you understand the things which others fail to show you. Okay, and the next one is, this is 0.789. 0.789. So I would say add. And then the last one, okay, last but not the least, is 0.793. 0.793. Add. And then the very last one is 797. 797. Okay, and say add. Okay, so I am not, sorry, I'm going to use a sweep plan. I am not going to do a sweep here, which is the standard sweep, and I'm going to hit simulate. Netlist parsing, just 1 second. Okay, let's hit simulate. Okay, no. So now you can see it more clearly. Okay, so this green one, I'm going to draw dotted. Dotted or short dash. Okay, so what do you see here? This is biased with the current, and this green one is biased with the voltage. And just plot the current now, this time, or the base current. Okay, so I'm going to add the base current from the biased with the voltage. Just plot the base. Okay, and this I'm going to plot on the right axis. Okay, and I will introduce a new axis if that is required. So let me put here a new axis. Okay, so I'm going to go here and say add axis, add a new y-axis on the right side, and say OK, and I'm going to plot this along the new axis. Okay, and of course, you know, I don't want to see this current because this part is not what I want to see. So I'm going to, okay, I'm going to put another x-axis. Okay, because I want to scale this, right? Or rather, that's okay. What I'll do here is I want to simulate for a longer duration. So let's simulate VC up to 3.8, for example. Okay, 3.8. Then it will be very clearly visible to you. No, So do you see that the current has become negative somewhere here? Okay, look at this axis. This axis is over here. So let me just, in case you get confused, let's put here a line. So you would observe, and let me also change the grid. Preferences, where is the grid? Grid snap. Okay, grid distance 0.0625, 0.0625. Okay, apply 1. Okay, and now I'll be able to put it down to 0. Okay, observe this, which nobody shows you in any of their books or in YouTube. Okay, you observe this, that this base current became negative somewhere here. Okay, why did it become negative? Because you are biasing with a voltage now, and the current is now able to flow into the voltage source, which earlier could not because it was a current bias. So current bias lets the VB swing, while a voltage bias will cause the negative base current to flow, so that the runaway doesn't occur here. Runaway will occur at much higher voltage. So what would be the much higher voltage? Okay, so the runaway occurs at much higher voltage, right? So this is what is the difference. The other difference would be, you would see if I zoom into this portion, if I zoom into this portion, you will see that the red one has lower slope than the green one. So let's zoom out a little. Okay, maybe it is not so well, but what happens is, over here you can see the red one has going to have a higher slope than the red one is going to have a lower slope than the green one. And why is that? The reason is that the base width modulation, okay, if you are purely varying collector base voltage, the base width modulation is going to be more in case you bias with a voltage. While the base width, because any change in VCE is the change in VCB, because VBE is held constant. So any change in VCE is change in VCB. So that means that the channel length the base width modulation is going to be more. But when you bias it with the current, VBEs can swing. So whatever is change in VCEs get divided over change in VCB and change in VBE. So that means that the transistor is going to be more linear if you bias it with the current source. But it is going to be less linear when you bias it with the voltage source. Now that means that when you design an amplifier, biasing with the current source will give you a more linear transistor. And when you are talking about breakdowns, then biasing with the voltage will have advantage because it will push out the thermal runaway. Okay, and then there is an intermediate way, okay, which I will show you here. That intermediate way is the following. You bias it with the current, right, but then you hang another transistor in here which is basically turned on, controlled by this resistor where it turns on. Okay, so as soon as you start getting the negative current, this voltage is going to be pushed down, and this, yeah, so okay, so when you start getting a negative current, this voltage is going to change, and you can decide where this this thing turns on. So basically, as soon as you start getting the negative current, okay, you take that current and have this is in here. So what is going to happen is the breakdown which you see here because of runaway is not going to occur, because the current is not forced to flow here, but the current takes the path to this transistor. So though biasing with the current gives you more linear transistor, but then you have arrangement to swamp all the negative current so that this breakdown can be shifted away. Okay, so now this is too much of a playing around, and this is the advantage of working with a simulator and a model over studying a book or learning the things from a professor. Okay, so a professor would not teach you this. Okay, so I'm going to end the session here. Thanks a lot. Thank you.